Hi, this is Kiffer with this week's lecture on nonparametric tests, where we'll discuss the Wilcoxon-Sign-Ring test, the Mann-Whitney test, the Kruskal-Wallis test, and the sign test. So starting on slide 2, we kind of introduced the difference between parametric and nonparametric tests. Now, perhaps the easiest way to think of this is parametric tests are for those which are normally distributed, use kind of the right data types like interval or ratio, don't have any outliers, and they kind of have equal variances between your two sets of observation. These are more efficient, they utilize all the data that you have, and are able to kind of obey kind of the classical laws of statistics that we've come to use in most of our work. But also there are data sets where that is simply not true, whether this is because of sample size or just because of the natural distribution of the thing, and these we refer to as nonparametric tests. And this can be when the phenomena that you're interested in is distributed bimodally or uniform distribution, where kind of the histogram is at all levels kind of the same, or skewed, as we kind of have pictured here on slide 2. These we call distribution-free tests because they don't utilize a distribution, because they don't use the values of the data, they use ranks, which we will talk to in a slide or two. But these are tolerant of non-normally distributed data. They can use things like ordinal and nominal data types, and they're more tolerant of outliers, and they also can allow for unequal variances. Some of them can. And so nonparametric tests are a good tool to add to your toolbox of statistical approaches, so that you can kind of get a good sense of what it is the data is trying to tell you. Of course, the problem with nonparametric tests is because they don't utilize as much of the information, is that they're somewhat less accurate, and so they require often a little bit larger sample sizes to kind of get as efficient estimates as the parametric tests can. But empirical examinations show that these nonparametric tests can in fact be equally reliable, assuming you power them sufficiently. And a couple weeks ago we talked about sample size and power for normally distributed variables, but there are also ways to calculate sample size and power for nonparametric, though those are probably beyond the scope of this course. In slide 3, I kind of introduced this concept, like I said I would, of ranks and versus values. Now, parametric methods use the values of a variable to kind of calculate a mean and that sort of thing, whereas non-parametric methods are concerned with not the value but the rank of a thing. So you can imagine that, say you had something like blood pressure or IQ scores or something like that, and the values would be like 121, 199, 123, and so forth. And that would be fine for a parametric test, but non-parametric tests do something special with those values. Instead of looking at the specific values, they just look at the relationship between them to give you a sense of what's called the rank. And so we calculate ranks by basically organize the values into descending order, so from low to high, and then we assign values, each value a rank. And for tied values, like you can see there's two 121s, for tied values we just split the ranks they would occupy. And so this is how you calculate a rank. And so on slide 4 you can see that a classical example of this is the median, which utilizes the rank order of values. To calculate a median, you organize all the data into from low to high, and then you count to the middle point, the 50th percentile, and that's your median value. You can see that in a normal distribution, the median and mean are approximately the same. In a perfectly normal distribution, they would be the same. But in a skewed distribution, the mean is tugged towards the outliers. And so, or basically just towards the tail. And this is what we called it right skewed, is when it's tugged right, and we call it left skewed when the mean is tugged left. And so the mean actually uses the average values, and the median calculates the 50th rank. And so median versus mean is a good way to kind of be introduced to parametric versus non-parametric measures. Mean is a parametric measure, and median is a non-parametric measure. Now in slide 5, I kind of introduced the basic tests that are used. Of course, we all know that there are lots of tests besides these, but for the sake of your texts, these are the ones that were generally considered. There's the independent t-test, the paired t-test, and one-way ANOVA. Now, those are just 3 different ways to compare either independent means, paired means, or multiple kind of groups, independent groups. And so, looking at this, we can see that the non-parametric methods line up with some of those other parametric methods. The Mann-Whitney U-test is an equivalent to the independent t-test for non-parametric data. The sign test and Wilcoxon signed rank test, those are both equivalent to paired t-tests. And the Kruskal-Wallis H-test is equivalent to one-way ANOVA. And so, in many cases, we can use a non-parametric method in the place of a parametric method if it doesn't meet some of the classical assumptions, such as normality, that we expect statistical tests to meet. So the first of these is known as the Mann-Whitney test, and we introduced this on slide 6. Now the Mann-Whitney test is also called Mann-Whitney U-test, or Mann-Whitney-Wilcoxon test, or the Wilcoxon rank sum test. And basically is what we do here is we take the values, we calculate their ranks, and then we plug them into these U formulas. And then we basically plugging just the sample size and the sum of the ranks from our 2 groups that are independent from one another. And you take the smaller of U1 or U2, and if it is less than or equal to the critical value, which you find in a table, which in your textbook, this is on page 344, then you can reject the null hypothesis if the smaller of U1 or U2 is less than or equal to the critical value you identified. And so this is a really kind of simple test. An example is on slide 7, where you can imagine if you're, say, comparing reading test scores for males and female second graders, you would look up first what is the critical value, and we go to the table at the end of the textbook, and we see that the critical value for this sample size and p-value that we're interested in is 1. And then you basically plug those factors into the formula as we have been doing for U1. You plug in the factors there into the U1, and then U2 you plug in the same things into those. Remember, the formulas are outlined on slide 6. And so you just plug the formulas in, and then you take the lesser of the 2 U's. Now we can see that the U2 was 15.5 and U1 was 4.5, and so your U here is going to be 4.5. So that's your test statistic. And remember from slide 6 that if U, or 4.5 in this case, is less than or equal to the critical value, you can reject it. However, because our critical value is 1, in this case we fail to reject. And so what this tells us is that there is no difference between the males and females in terms of their reading test scores in this small sample. And so that's a helpful way. This sample size is probably too small to conduct a traditional statistical method on. And so that's what nonparametric tests can help you to do. So the next one is a sign test. Now the sign test compares 2 pair groups, and what it does is ultimately it's an easy kind of 4-step approach. No formula is even required in this one. You just calculate the difference between each pair, because you can imagine, say you're doing pre and post testing, you would calculate the difference between post-test and pre-test for each matched, or maybe these are 2 individuals that you matched up based on certain characteristics. But then you count the number of positive differences in step 2, and then you count the number of negative differences, and that's basically just looking at the sign of the calculated difference that you calculate in step 1. And then you determine if the smaller of the values from step 2 and 3 is less than the critical value, which again, the critical value, you can look that up in a textbook or other tables For this one, the textbook has a sign test table on page 346, and if the test statistic, which is the lesser of negative or positive signs, so you're just counting up the signs, which I'll show you an example in the next slide, is less than or equal to the critical value, then you reject the null hypothesis. And so this is a fairly simple test. And so on slide 9, you can imagine that if we're comparing depression scores before and after 8 sessions of something like cognitive behavioral therapy, that we can calculate those differences. Remember, that's step 1, and so 53 minus 49 is 4, and 52 minus 48 is 4, and 44 minus 41 is 3, and so on and so forth. And that's your ranks, or sorry, your differences. And then those differences, you can see that, for example, the 5th one down there is 50 minus 54. That results in a difference of minus 4. And same with one up from the bottom there, -8 and -1. And then as simply as all we do, remember step 2 was to count the number of positives, which in this case it's 1, 2, 3, 4, 5, 6. And we count the number of negatives, which is 1, 2, 3. And whichever of those two is fewer, 3 is less than 6. So 3 is our test statistic. 3 is indeed, for a two-sided test, alpha 0.05 is indeed larger instead of smaller than 1, and therefore we fail to reject the null hypothesis. And so again, this shows that there's no difference between the pre and post test. And so that's what the sign test is. And related to the sign test, also used to compare two paired groups. On slide 10, we introduced the Wilcoxon signed rank test. Now, the Wilcoxon signed rank test has a similar value. It's slightly more complex than the sign test. But in step 1, you calculate the differences between each pair. And so if this is a pre-post test, then you would subtract the pre-value from the post value. You order those values, ignoring the signs, and so you order them all together. And then you, what we call assign ranks. Remember how to calculate ranks. It's just ordering the data, and then, counting them up. And whenever you have a tie, you break it by averaging the two ranks that it would have occupied. And then in step 4, you sum together the positive signed ranks. And step 5, you sum together the negative signed ranks. And then step 6, you determine if the smaller of the values from step 4 or 5 is less than the critical value. And if it is, then you reject the null hypothesis. And so an example of this, of course, is on slide 11, where we're comparing the depression scores before and after of 8 sessions of cognitive behavioral therapy. We look up the critical value from the textbook. In this case, it's 8 for a Wilcoxon signs rank test for a two-sided test at alpha equals 0.05. We look at these two values at pre-test and post-test. We calculate the difference. Differences being 4, 4, 3, 5, -4, 1, -8, 1, and 1. And then we reorder those, and remember, from low to high. And so if you reorder those, we have -1, 1, 1, 3, 4, 4, -4, 5, 8. Because remember, if you look back, you ignore the signs when you order them in step 2. And then once you've ordered them, you assign them ranks. Because there's a tie at -1, 1, 1, you would assign that rank of 2. If there's a tie at 3, if there's a tie again at 4, 4, 4, so you assign those an average of 6, because those are the ranks they would have occupied. So if you were just kind of randomly assigning in those groups, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. But because the spots in 1, 2, and 3 all tied, and the spots in 5, 6, and 7 all tied, you simply tie it to, you simply average those to 2 for the first 3. 4 gets 4, and then the next 3 get averaged at 6 instead of doing 5, 6, 7. And so this gives you ranks, and then simply you calculate the sum of the signed ranks. And so for the negatives, it's -2 plus -6 plus -9, which equals 17. and then the assigned rank for the positives is 2 plus 2 plus 4 plus 6 plus 6 plus 8, which is equal to 28. And so the smaller of those two, remember that's how we determine is the smaller values from step 4 and 5. And we see that that is 17. And so in this case, we fail to reject because the critical value is less than the test statistic. And remember, in order to reject the null hypothesis, the W, whichever of the two is smaller, has to be less than or equal to the critical value, which you find in the textbook. And so that's, again, very simple calculations and helps you to kind of understand how these are working. They're working based on ranks, not on values, because with the values, you're assuming some sort of normal distribution. With the ranks, you're just comparing, well, are the distributions the same? You don't need to know necessarily whether or not they fit into a normal distribution. You're losing that sense of information, but you can at least get a sense of, well, how big of a difference are these two distributions based on the median values. And so the next one of these is the Kruskal-Wallis H-test, which this is used to compare 3 or more groups, so getting a little bit more complex. Here we introduce a formula again, which is available on slide 12. For this, the first step is to combine all the data into a single ordered list. So you order them, and then you rank them using the same ranking techniques that we introduced on in the first few slides there. And then you separate the data back into groups with their ranked values, and you just calculate the H statistic, which is pretty easy. All it includes is the formula requires you to know the total sample size, the number of groups, the sum of ranks in each group, and the sample size in each group. And then you can reject the null hypothesis if the H-test is greater than or equal to the critical value found in your textbook, in this case on page 348, table 8. And in this case, you can see that I bolded and underlined greater than, because the other ones required you to reject the null hypothesis if the test statistic was less than the critical value. Here it's that it's greater than. And so an example of this is on slide 13, where we compare, say, the acceptability ratings ranging from 0 to 10 for an intervention among 3 groups. Each group, for the sake of simplicity, is of equal sample size, and 1 equals 3, and 2 equals 3, and 3 equals 3, and you were doing it at alpha 0.05. And so the critical value I looked up from the textbook is 5.6. And if you go look at that critical value table, this thing is pretty easy to interpret. It just has the sample size for each one, the alpha that you're interested in, and that allows you to kind of grab your critical value, and then you calculate the test statistic. Again, it's one of our standard formulas. We're just plugging and playing. We plug in the total sample size there in the first part of the equation, and then you plug in the sum of ranks for the top, and then you plug in the sample sizes for each. Sum those together. That's what on the last slide, that's what the kind of big E thing means. It means summing those values together. And then you just finish off the last part of the equation by again plugging in the total sample size. This, if you do the math here, and I encourage you to practice doing the math, and there's some practice equations for you to do so at the end. But ultimately we get an H statistics of 0.06, and so that is smaller than the test statistic of 5.6. And remember, this test requires the test statistic to be greater than the critical value in order to reject the null hypothesis. However, this was not the case, and so again, we failed to reject. And so it didn't look like any of the 3 interventions had higher acceptability or lower acceptability than the others, even though we do see that group A did have differing acceptability, but overall this was not considered statistically significant even by a non-parametric test. And so in review, on slide 14, we kind of see that these 4 tests are alternatives to the parametric tests that we use when we have a normal distribution and when our data kind of meet our standard statistical assumptions. There are other non-parametric tests out there to be aware of. The Spearman's rate correlation, for example, replaces Pearson correlation. However, the same basic principles apply. Here we're concerned with ranked data, which, because we're kind of losing the value, we're losing information, we're losing specificity in the data, and therefore they become less efficient. And so obviously, if possible, you can use a parametric test. You want to meet those kind of classical statistical assumptions. But non-parametric tests provide a good alternative to help you kind of understand the world and the different varying data sets that you're looking at. And so with that, I'll leave you to the study guide. I've provided some questions here on slides 15, 16, where you can practice a Mann-Whitney test, slide 17, where you can practice comparing a baseline test measure, basically a paired test, and then in slide 10, slide 18, question 10, you get to kind of practice doing a Kruskal-Wallis test with 3 groups looking at exercise. And so these should give you examples in the kind of comment section of the notes on the PowerPoint. You can click on those and see where I kind of pulled those data from. Some of the questions might not match exactly the example question given. I tried to adapt them for health, but that'll give you at least the numerical answer that you're looking for, assuming I copied everything over correctly. And so with that, I'll leave you to it and look forward to seeing your questions on the discussion board.